Let's start the video. So under operator, the definition of an operator, how to define an operator. An operator A cap is the mathematical rule that when applied to a ket psi, transform it into another ket psi prime of the same space. And when it acts on a bra, it transforms it another bra. So if operator A operates on psi, then it transforms psi into psi prime, and if operator operates on bra phi, then it transforms it into bra phi prime of the same space. There are some examples of operator which we are very which are very useful in the study of quantum mechanics. First is unity operator. So unity operator when applied on any ket, it leaves unchanged. That is, if unity operator I cap is applied on any ket, so ket psi remains unchanged. Next is parity operator. Parity operator if parity operator p cap is applied on any function psi r, then it transforms it into psi minus r. Next operator is the gradient operator. So gradient operator del, if it is applied on psi function, then it becomes del by del x psi I plus del by del y psi r j plus del by del z psi r k. And the next operator is a linear momentum operator, that is linear momentum operator. So linear momentum operator P when applied on wave function, then it becomes minus I h cross del psi r, which can also be written as h cross by I del psi r. And the next operator is Laplacian operator. Del square. When it is applied on any function psi, then function becomes del 2 by del x square psi plus del 2 by del y square psi plus del 2 by del z square psi. These are the operators which we use in the quantum mechanics. Now the proper now we learn about the product of operators. So under product of operators, the product of two operators is generally not commutative. So if there are operator A and operator B, then their product operator A into B is generally not commutative. That is, if we change their order, the meaning or value of the operator may change. But the product of operators is associative. So product of operators is associative. Like if we have three operators A, B, and C, then operator A into operator B into operator C is equal to operator A into operator BC is equal to operator AB into C. In generalized sense, we can also write A operator to the power n into A operator to the power m is equal to operator A to the power n plus m. When the product AB operators operates on a Kate psi, the order of the application is very important. That is, operator in the operator AB, the operator B operates first on any function state vector Kate psi, and then operator A operates on new Kate B psi. That is, if operator AB operates on Kate psi, then it is equal to operator A operates on B Kate psi. So order of the operator is very important. Similarly, if there are more than two operators operate on a state psi, then suppose if there are four operators in product and they operate on Kate psi, then the operator, sorry, this is D. Then the operator D operates first, like this. A operator B, operator C, D operates on Kate psi, and then operator C operates on the Kate D psi, and so on. And lastly, A operates on the final B, C, D psi Kate. When an operator A is next, when an operator A is sandwiched between a bra and a Kate psi, then it yields a complex number. That is, you know, bra phi operator A ket psi gives a complex number. The quantity bra phi operator A ket psi can also be purely real or purely imaginary, but in general it is a complex. Now we will learn about the linear operators. An operator A is said to be linear if it commutes with constants and obeys the distributive law. So, if operator A is said to be linear, then it must commute with the constants and it obeys the distributive law. That is, an operator A is linear if for any vector psi1 and vector psi2 and any complex number a1 and a2, we have operator A operates on a1 ket psi1 plus a2 ket psi2 is equal to a1 operator A ket psi1 plus a2 operator A ket psi2, that is distributive, and bra psi1 a1 plus bra psi2 a2 operates by A is equal to a1 bra psi1 operator A plus a2 bra psi2 operator A. So you should note that we always, in the case of bra, we keep the operator in the right side. We keep here. We can't keep here. That is not allowed. Only we keep after the bra. It to be correct. It is worthy to note that the expectation or mean value of an operator with respect to any state vector ket psi is defined by ket psi bra psi operator A ket psi. So this gives the expectation value or mean value. Further, the quantity ket phi bra psi is a linear operator. And it is also an operator in Dirac's notation. So here we found that ket phi bra psi, then we can treat it as an operator in Dirac notation. If you want to see how it operates, then let's check. When ket phi bra psi is new ket applied to a new ket psi prime, then we have another ket. How? See, ket phi bra psi is operating on a ket psi prime, which is equal to bra ket psi prime ket phi, where this is a complex number. This is a complex number. So definitely we have a new ket with some expectation value. That means this operates as an operator on the ket psi prime. Product of the type ket psi operator A and operator A bra psi operator A bra psi is not allowed. That is forbidden. They are not operators or kets or bras. They have no physical meanings. So friends, now we will study about the Hermitian adjoint. So Hermitian adjoint is an operator that is written as a dagger. A dagger. Hermitian operator adjoint is written as a dagger, and it is a complex conjugate of the number. The Hermitian adjoint or conjugate a dagger of a complex number A is the complex conjugate of this number. That is, a dagger is nothing but is equal to complex conjugate of the A number. Hermitian adjoint are simply the adjoint and of an operator is defined by this relation. Suppose we have a operator A. So Hermitian adjoint of this operator A dagger is defined by bra psi A dagger ket phi is equal to bra phi operator A ket psi complex conjugate. So see the order. The order is important. You can see that A dagger adjoint Hermitian adjoint is defined by this relation, and it is now the properties of the Hermitian conjugate. The term adjoint and conjugate are used indiscriminately. That means Hermitian conjugate or Hermitian adjoint is the same thing. Now to obtain the Hermitian adjoint, of any expression, we must cyclically reverse the order of the factors and make three replacements. First, replace constants by their complex conjugate. Constant by their complex conjugate. Second, replace kit by their corresponding bras, or their are bras by their corresponding kit. And replace the operator by their adjoints. So if you want to get the Hermitian adjoint of any expression, so we must have to apply these three order: constant by their complex conjugate, bras by their corresponding kits, and kits by their corresponding bras, and operators by their adjoint. We can see if A operator A dagger, then we can write this as A dagger into A dagger is equal to A complex into A dagger. If operator ad, ad, sorry, if adjoint is written like this, adjoint of adjoint is equal to operator. If the summation of 2, 3, 4 adjoints are given like this, adjoints of summation of the operator is equal to the summation of adjoint of the corresponding op operators adjoint. If the adjoint of the if the adjoint of the product of operators is given, then we can write this in reverse order first, and then we replace the operator with their corresponding adjoint. So follow carefully the sequence. If any vector, if any operator n, then the adjoint of operator to the power n is given by adjoint operator to the power n. Now, further, now if the adjoint of the product of operators applied on the kit psi is given, then this can be written as bra psi, and adjoint of the operators in the reverse cycle, that is dagger D, dagger C, dagger B into dagger A. The Hermitian conjugate of the operator like this. If this is an operator, then we want to adjoint of this operator. If one the adjoint of this operator, then this can be written as ket psi bra phi adjoint is equal to bra phi, sorry, ket phi bra psi. So you can see that the ket becomes bra and bra becomes ket in the opposite order. Also, it is to be noted that so we should not be confused like this with these things like ket of alpha operator A is equal to alpha operator A on ket psi, and if bra alpha A psi is equal to alpha conjugate bra psi operated by the operator. So we should be cautious with these things. If alpha is with the ket format, then it will be simply out, and if alpha is within the bra format, then it will be coming out with its conjugate values. Now, Hermitian and skew Hermitian operators. Any operator A is said to be Hermitian operator if it is equal to its adjoint, or bra psi A ket phi is equal to bra phi A ket psi complex conjugate. On the other hand, if any operator B is said to be a skew Hermitian operator if it is not equal to its adjoint, that is B dagger is not equal to its adjoint, that is it is equal to the negative. Therefore, also R bra psi operator ket phi is equal to minus bra operator ket psi complex. So we see here that in the case of the non-Hermitian operator, that is a skew Hermitian operator, we are getting the negative sign. It is not equal to its adjoint. We should note that momentum and position operators are Hermitian operator. That is, if x is a position operator, then x dagger is equal to x. And if P is the position, if P is the momentum operator, then P dagger is equal to H cross by I del dagger is equal to operator P. They, that is, they are equal to their corresponding adjoint. So position momentum operators are Hermitian operators. It is important to note that the Hermitian adjoint of an operator is not equal to its complex conjugate. Hermitian adjoint of an operator is not equal to its complex conjugate. In general, they are not equal. For example, the momentum operator is Hermitian, yet its complex conjugate is not equal to it. That is, if P dagger is equal to P, but P complex conjugate is equal to H cross by I del complex conjugate is equal to minus H cross by I del, that is equal to minus operator P. So we know that P is the Hermitian operator, but it is not equal to its complex conjugate. But in the case of position operator, it is Hermitian, as well as the complex conjugate of the position operator is equal to the position operator. So we can't generalize this rule. Some operators are equal to their complex conjugate and some may not. Now we learn about the projection operators. An operator P is said to be a projector or projection operator if it is Hermitian. If it is Hermitian, that is P dagger is equal to P and is equal to its own square, that is operator P is equal to P square. So these two conditions should be fulfilled for an operator to be a projector or projection operator. There are some important properties of the projectors. The first property is the product of two commuting projectors P1 and P2 is also a projector. That is, product of two projection operator P1 and P2 is also a projection operator. So that should be equal to P. So P2 dagger into P1 dagger is equal to, since P1 and P2 are individually projection operators, so that will be equal to P2 into P1 is equal to P1 into P2. And again, their square should be equal to its own value, that is P1 P2 whole square is equal to P1 P2 into P1 P2 is equal to P1 into P1 P2 into P2 is equal to P1 square P2 square is equal to P1 P2. So these P1 P2 projection operators gives their product also as a projection operator. The summation of two projection operators is generally not a projection operator. Second point is the summation of P1 and P2 are two projection operators will generally not give the P1 plus P2 in general. The two projection operators are said to be orthogonal if their product is 0. So if P1 and P2 are two projection operators, then they are said to be orthogonal if their product is equal to 0. A sum of projection operator to be a projection operator, it's necessary and sufficient that these projection operator must be mutually orthogonal. So this orthogonal properties implies that if there is a sum of projection operators and for their sum to be a projection operator, it is projection operator, it is necessary and sufficient condition that these projection operators be mutually orthogonal. These should be orthogonal to each other. Now we will study about the commutator algebra. Friends, before starting the commutator algebra, I would like to request you all, if you like this video, please press the like button and share with your friends so that they can also learn about this topic. Friends, if you are watching for the first time, then please subscribe the Sciacademy channel so that you can get the notification of the upcoming videos on time and you could not miss the coming videos. So friends, let's start the commutator algebra. The commutator of two operators A and B is denoted by square bracket operator A comma operator B. So A and B are two operators and their commutation is denoted by square bracket operator A comma operator B and is defined by operator A into operator B minus operator B into operator A. Similarly, we define the anti-commutator as the square bracket A comma B is equal to operator A into operator B plus operator B into operator A. So friends, notice here this is the plus sign in the case of anti-commutator. So these are commutator and these are anti-commutator. So that's why plus sign. Two operators are said to commute if their commutator is equal to 0. That means if A and B are two operators and they commute, then their commutation relation square bracket A comma B is equal to 0. That means AB minus BA is equal to 0. That means operator A into B is equal to operator B into A. Any operator commute with itself. That is, if A is any operator, then operator then commutator A comma A is always equal to 0. It is important to note that if two operators are Hermitian and their product is also Hermitian, then these operators commute. That is, dagger of A into B is equal to B dagger A dagger is equal to B into A. And since AB dagger is equal to AB, as their product is Hermitian, so we have AB is equal to BA from this and this. There are some basic properties of commutators. As you know that commutation relation of any two operator A and B is given by square bracket A comma B is equal to AB minus BA. So these commutators have some basic properties, like they have the properties of antisymmetry. They are antisymmetric, that is, a commutation relation of A comma B is equal to minus B comma A. That is, if you change the order of A and B, then they are not exactly equal, but the relation become negative. That is, they are antisymmetric. Commutators are antisymmetric. Second property is linearity. They follow the principle of linearity, that is, commutation relation of A with the summation of B, C, D, and so on is equal to commutation of A with B plus commutation of A with C plus commutation of A with D plus so on. So they follow the linearity. Third, Hermitian conjugate of a commutator can be written as Hermitian conjugate of commutator is equal to commutator of B dagger A dagger. So Hermitian conjugate of a commutator can be written as the commutation relation of the B dagger A dagger. Fourth, distributive principle. So if A comma B C, then it is equal to A commutation with B into C plus B commutation of A with C. That is, they follow the distributive principle. So basically this is the distributivity with addition, and this is the distributive with the multiplication. Next is Jacobi identity. That is, if A comma B C plus B, comma, commutator of C and A plus C, A, B. This is equal to 0. This is known as Jacobian identity. Next property is operator commute with the scalars. That is commutation relation with of A with B, a scalar, is 0. So these are the some basic properties of commutators. Now we will study about the uncertainty relation between two operators. So let's start. Friend, before that, I would like to request you that if you like this video, please share and subscribe the channel. So friends, an interesting application of the commutator algebra is to derive a general relation of giving the uncertainties product of two operators A and B. So let A and B are two Hermitian operators, and expectation value A and B are the expectation values of operators A and B respectively. That is, expectation value of A is equal to pra psi A ket psi, and expectation value B is equal to bra psi B ket psi, where ket psi is a normalized state vector related to these operators. Now the uncertainty is defined by the uncertainty delta A is equal to square root expectation of A square minus square of expectation. Similarly, uncertainty in B is defined as square root expectation of B square minus square of expectation B, where expectation of A square can be written as this, and expectation of B square can be written as so. where delta A is equal to A minus expectation of A and delta B is equal to B minus expectation of B. So this is equation number 2, and I will put the previous equation as equation number 1. Now assume that the action of the operators delta A and delta B on any state psi is given by delta A ket psi is equal to chi and delta B on ket psi is equal to ket phi. So let us assume this is equation number 3. Now we will write Schwarz inequality for the states. The Schwarz inequality for ket chi and ket phi is given by greater than equal to modulus square so this is equation number 4. Now since A and B are Hermitian, delta A and delta B must also be a Hermitian. So that delta A dagger is equal to A minus expectation A dagger is equal to A dagger minus expectation A, which is equal to A dagger is equal to A dagger minus expectation A is equal to A minus expectation A, which is nothing but delta A. Therefore, we prove that delta A is the Hermitian. Similarly, we can prove that delta B dagger is equal to delta B. So, using the Hermiticity of delta A and delta B, we can verify that and these are equal to ket psi del A whole square plus psi and ket psi delta B whole square psi respectively. As delta A dagger is equal to delta A, so delta uh, brass sky with this kit chi is equal to, substituting these values, del A dagger into del A therefore brass psi del A whole square kit psi is equal to expectation of delta A whole square. Similarly, we can write for the bra phi with kit phi is equal to expectation of delta B whole square. Now this is therefore the equation 4 reduces to equation 4 reduces to expectation of delta A whole square into expectation of delta B whole square is greater than equal to modulus square expectation of delta A into delta B square. So this is equation number 5. Now delta A into delta B can be written in terms of commutator and anti-commutator as given below. So delta A into delta B is equal to half delta A into delta B commutation plus half anti-commutation delta A into comma delta B, which is equal to half A B plus half anti-commutator delta A delta B. We have written this equal to this. Now since Commutator AB is anti-Hermitian, and anti-commutator delta A and delta B is Hermitian. Therefore, since the expectation value of a Hermitian operator is real, so expectation value of this delta A comma delta B is real, and expectation value of anti-Hermitian is imaginary. So this is equation number 6. Now we will find the expectation value of 6. So expectation value of this is equal to the expect sum of the real part of this and sum of imaginary part of this, that is equal to the square of this expectation value is equal to 1 by 4 expectation value of AB square plus 1 by 4 expectation value of delta A comma delta B square. Since the last term is positive real number, this is real, as this is real, so this is positive and real number. Therefore, this equation is greater than this value. Expectation of modulus square of expectation of delta A into delta B square is greater than equal to 1/4 of the modulus square of expectation value of commutator A B. So this is equation number 8 and this is equation number 7. Now comparing equation number 5 and 8, we get delta from 5 and 8. We get expectation of delta A square into expectation of delta B square is greater than equal to 1/4 of the expectation modulus square of expectation of A B commutator. Since expectation of delta A square is equal to expectation of A square plus expectation of A whole square minus 2A into expectation of A, this using equation number 2, which is equal to A square expectation minus square of expectation A. Now combining this with equation number 1, this leads to expectation of delta A whole square is equal to delta A whole square. Thus equation. So this equation number 9 becomes delta A into delta B is greater than equal to 1 by 2 modulus of expectation of A B, and this is the uncertainty relation between two operators. This uncertainty relation plays an important role in the formalism of quantum mechanics, and its application to position and momentum operators leads to the Heisenberg uncertainty relationship delta x into delta px greater than equal to h cross by 2, and delta y into delta py is greater than equal to h cross by 2, and delta z into delta pz is greater than equal to h cross by 2. So this is the uncertainty relation between two operators. So friends, I hope that you enjoyed this video and learned about all the points which I covered in this video lecture. So if you enjoy this and like this video, please press the like button and share with your friends. And please, if you are watching for the first time, subscribe the Sciacademy channel. Stay tuned. Thank you.